So I think it's the time to move on to the next talk. The next talk will be given by Dr. Tong from the University of Hong Kong, and with the title of Support to Robotic Hand for Stroke Rehabilitation. So Dr. Tong, it's your stage.
Yeah, thank you for the invitations. And then today I would like to share about the soft robotic that we explore in our laboratory. So I think all of us know about stroke is the top 2 killers in the world. Every 6 seconds, one person has stroke. So it's, I think you can imagine how difficult if the hand cannot move properly after stroke, you know, and a lot of activity have been affected in their daily life. Even pick up a glass of water. So it's, there's a lot of different systems for the elbow, shoulder, you know, but the hand is one of the most important part. But as we all know, the hand is the most difficult part to get rehab after the stroke. So this is my team, and then thanks for all the funding. So let's see what we can do with the robotic system. We begin with some of the big systems like this gate trainer from Germany, and later on we build our own robot towers, and that one using the EMG to drive the systems. And then later on we have this hand of hope. It's using the EMG from the affected side to drive the robot hands to open and close. And then later on we have this ankle robot, knee robot. But recently we moved to the soft robotic and shoulder robot. And then why we move from the hand of hope to soft robotic, because we found out this for those mechanical robots, it's very difficult to pick up small objects. But for the occupation therapists, they want to manipulate objects during the rehabilitation. So we want to do that. And the other reason is we also entertain some of the stroke survivor is very young age, something like 4 years old. You know, so those kids very difficult with the mechanical robot. And now we can use this 3D printing, soft robotic hand, we can conduct those rehabilitations. So this is some of the information about the EMG-driven robotic system that we build. One thing we learned from this setup is if we just have a passive robotic training, actually the stroke survivor brain cannot learn all these new tasks. The brain didn't evolve. But if we use the human intentions, just like the previous speaker, using the EMG to drive the system, actually it helps the brain to motor relearn. And then this is important part. So the EMG plus the motor actually have a better recovery in our findings. So this is the papers that we have conducted training on the wrist joint. And then we find out this EMG driven with the robot is have a better recovery for the motor relearning. And after 27 training, we can see the clinical score improve. They were discharged for 3 months and come back for the follow-up assessments, and we can still see the improvements still exist after the training. But when we look at the other one, just is a randomized control trial. The other one just look at the passive robot training. What we can see is just a reduce in the spasticity from the wrist. There's no motor coordination improve, but the worst thing is after 3 months, they come back from the follow-up, and then the spasticity come back. So we notice the human intentions like the EMG or EEG drive with the robot is important for the motor relearning from our finding. So this is the hand of hope, but what we want to do is how to make it become more soft, and then rather than just pick up as big objects. So this is how they pick objects. Before we cannot pick a very, very small objects, just like the spongy, they can pick because that can be deformable, you know. But the small objects, the mechanical structures cannot do all these tasks. Even for the mechanical structures, and then we can see a great improvement in the hand functions. So it's very good. We can see from the ARAT, we can see the motor recovery in the hand and finger functions that we haven't seen before in the wrist and elbow robots. So this is very remarkable. But we want to further improve the finger dexterity, and then we want to use the soft robot to accomplish this task. We can see it all around the world. In Singapore, they have a very nice system and then that then facilitate the stroke survivor to grab the objects, grab some small objects using this soft robotic. But this is very difficult to open the hand, with this glove, and they have a new versions, but it's more the bigger size, So we have a think about whether we have another design we can do that. And the other thing is, it seems the system is using the passive training, but as I mentioned earlier, maybe the EMG-driven active training is more effective, So there's something we integrate in our system. The other one is from the Korea. They also use this sensor to sense the fingers open and close, but they don't have assistant. So as I mentioned, we need to have the EMG, human intention, together with the robot. Just the intention maybe not good enough. And the last ones maybe is more promising. They use the brainwave to control the soft robotic, and they also have this FDA approved. So this may be the direction we should go ahead, using the brainwave or the EMG to drive the soft robotic hand. So let's see what we have built in our lab. So this is the soft robot hand, the latest ones. So we use this soft elastic composite actuators. So we use this polymer to build together. And then there's a chamber. We have this pressurized air. We can flex the fingers. At the same time, the designs can help to open the fingers at the same time, because a lot of subjects have this spasticity. So open the hand edges is important. So you can see right now with our designs, they can pick up different objects. So later I can show you some of the video how we did that. The other thing is because the whole designs can be 3D print. And then so we can also entertain the young kids like 2 years old or 4 years old in our lab. So this is some of the reference. We publish soft robotics. You can have more details in our design. So we did some of the experiment tests. We apply different pressures, make sure the force is enough to grab the objects, and then to open the hands. This is very important in the system design. The other thing is that we want to make it portable. So you see now on the tables, we just have a small palm, and then there is sufficient enough to actuate our finger system for the soft robotic hand. But the other biggest challenge is not just close the hand in some system. It's because there's stroke subjects. Most of them have the spasticity. So we also create some of the systems to look at the stiffness of the fingers. So if there's a higher spasticity, like the MAS modified hour score is 2 or 3, it's very difficult for all the soft robot to move. But in our designs, we are able to do that. So actually, we have elastic material here, like a spring to help to open the hand. And then if they have a stronger spasticity, we can using much higher, the spring to help the subjects to open the hands. And then together with the actuator, you can see the P here is to pressurize the chamber. Actually, we can do this open and close actions. And then at the end, the beauty of this is we can also evaluate the spasticity of the fingers, because when we move, we know how the movements, and then we also can measure the pressures. Actually, we can estimate what's the spasticity level from our system that we haven't seen in other systems. So it's, now we can control the robots under the finger spasticity. At the same time, we can also do some clinical assessment with our system. So let's see some of the videos and then to see how the system works. So they're all stroke survivors, and then maybe some is with a brain injury, like the small kids here, 4 years old. So what we can see here is they can use this soft actuators to pick up objects, and our system using the EMG to drive the system. So you can see there's some electrodes here, and then with amplifiers for 1,000 times to amplify the EMG, and then they can drive the robot hands to open and close. So if they don't have any EMG signals to activate, the hand will not close the hand. So the closing and open the hands is actually depend on the residual EMG signal from the affected forearm. And then you can see that they can all control and then manipulate different objects. So we can achieve what we haven't been able to do it with the mechanical designed hand of hope. The next stage is we also conduct clinical trial to see the effect. So we have 16 chronic stroke survivor, and then we conduct a 20 session of EMG training, and then we have this assessments before and after the training and see the effect. And from our observations, and we find the ARET, BBT, and then also the grip strength have been improved, and then the improvement is bigger than the previous mechanical robotic hand. So that's very good. And the one more important thing is that this system also can be applied with more severe spastic subjects like the MAS S2, and then they can activate with this soft robotic hand. I think a lot of systems may not have sufficient power to do that. And then because it's soft robotic, so it's the system also very comfortable because they don't have this mechanical structures with it. So it's even they have a strong spasticity. They wear this soft robotic hand. They can gently to hold on their spastic hand. So this is also one of the advantage of the device. So the clinical trial is still ongoing, but the preliminary data is promising. And then we also publish some of the data in this journal article. If you want more information, actually, we have our file with the patent in US, and then you can see how it's our designed, and also we have some of the others publication about how we design this 3D printing and how we control this soft actuator, because fine controls to pair object is important. So we also have more information how to control this soft actuator and deal with those non-linearity. Because of interest time, and then I think I will stop here. So thanks. And then welcome any questions.